I guess we'll start now. So welcome to lecture 11. Um, Today starts another really interesting topic in linear algebra, um, which is the concept of eigenvalues and eigenvectors. I did post the notes in the chat recently if you want to follow along with the slides. But yeah, I'm excited to present today. So let's start with something we talked about last week, which is this homogeneous linear equation that we talked about. So basically throughout the whole lecture today, we're just going to assume that A is an n by n matrix. I think for the beginning, it's just kind of any matrix, but towards the middle, we'll start talking about it as being n by n. And generally thinking about square matrices is a good first step for thinking about things. But yeah, in particular, we are very focused right now on these square matrices. So the null space of the matrix A, to remind you, is the set of all solutions to the problem A times x equals 0. Now, we can do a little bit of rewriting. Any vector, if we scale it by 0, we get back the 0 vector. So we could have written this, that we want all solutions to ax equals 0x. And so, this is one way to think about the null space problem. It's what vectors are there where if I multiply them by a, it's the same thing as multiplying them by 0. But we don't have to just put a 0 here. We could put any number we want, and that's what we'll be talking about today. And this is called the eigenvalue problem. Now, so the eigenvalue problem is just what we were saying. You've got a system of equations, ax equals lambda x. So that little like upside down y looking thing is lambda. And it's just some number that we've picked. It could be 0, it could be 1, it could be a billion, it could be 4. It could be pi, anything. And we want to see, first of all, if this system of equations has a solution, and if it does, what are the solutions? So this is the eigenvalue problem, as I said, but you only can only phrase the eigenvalue problem if the matrix is square. So we're just going to talk about square matrices from now on. Now, this whole problem is called the eigenvalue problem, but there are really two parts to it. And these names are not standard, but I'm going to use them. The two questions are the eigenvalue candidate problem and the eigenvector problem. The first one is, can we figure out which values of lambda are such that there exists solutions to this problem? Now, one thing to note here, if I plug in 0 for x, so if I plug in the 0 vector for x, then the left-hand side will be 0. And the right-hand side will also be 0 because any number times a 0 vector gives you back the 0 vector. So x equals 0 is always a solution. And so what we're really looking for is what we call non-trivial solutions, because x equals 0 is the trivial solution to this problem. And so yeah, the first problem is to figure out which lambda have non-trivial solutions. And the second problem is, if you hand me a lambda, can I tell you all the solutions to that problem? And it turns out that the second problem is significantly easier than the first problem. And all we do to start out is we do a little bit of algebra. If you give me some lambda, then I can write the eigenvalue problem, which is equation 4. And this is the same thing as multiplying lambda times the identity matrix times x, because identity times x is always equal to x, so we can always add it. Well, and then we can subtract the right-hand side to get this equation, and then we can basically factor out these matrices, right? And so now we've stated this original eigenvalue problem into this new problem, and this is a null space problem, right? If you just replace this matrix here with like some matrix B, you now have the null space problem bx equals 0. And I forgot to put an n there, but this is the 0 vector. So we know how to solve these. We talked about solving them the other week. So you can, given a lambda, just use the same techniques we've been using for null space computations to figure out what the eigenvectors are. And so we call this set, the set of all x that solve the eigenvalue problem ax equals lambda x, we call those the eigenvectors of A with respect to lambda. And the set of all solutions to the eigenvalue problem, so the set of all eigenvectors, is actually a subspace of Rn. Because if you remember, when we talked about null spaces, we said, well, a null space is a subspace. And so we can compute the eigenspaces by computing a null space, which means that these must both be spaces. And so we call this the eigenspace of A corresponding to lambda. And yeah, are there any questions about what we've talked about so far? Okay. So moving on then. This brings us to the eigenvalue candidate problem, which I talked about, which is like, which values of lambda have non-trivial solutions? So I'll give you an example of an eigenvalue problem, which is, you can think about the problem identity times x equals lambda x, right? Now here, the only lambda where this is going to have a non-trivial solution is going to be lambda equals 1, because otherwise you'd have identity x equals lambda x, which means x equals lambda x, which means that either lambda equals 0 or x is 0. Sorry, either lambda is 1 or x is 0. So there's a question in the chat which was, why can't we just subtract the right-hand side without multiplying by the identity matrix? We can. The problem is, if we do that, then this won't be a matrix. This will be well, you cannot really subtract a scalar from a matrix. So you'd basically be stuck at this step, and you'd have to replace by an identity matrix anyway. Because we can only subtract matrices. We cannot subtract we cannot subtract lambda from A. Because they're not both matrices. Does that answer the question? Okay. So yeah, so we want to solve this eigenvalue candidate problem. But before we start doing this, I want to kind of ask a potentially interesting question, which is like, why does this eigenvalue candidate problem need to be solved? Well, I already gave you one example where you have a matrix and there's only one lambda where this problem is interesting, which is the identity matrix. And so the question is like, why do we in general expect that only some values of lambda will have non-trivial solutions. And the result that we're going to talk about is that actually, if A is an n by n matrix, then at most n different values of lambda have non-trivial solutions. And we're actually going to go through almost a formal proof of that result, which I think this may be the first time we've like presented a full proof in lecture, but I felt that it was necessary, or I guess that I have presented one, I should say. So we first need to talk about this idea called linear independence, which is I have not mentioned it before, which is that if we have a list of vectors that are all the same size, we say that they are linearly dependent, so not independent, dependent, if when you make the matrix whose columns are those vectors, then the null space problem has a non-trivial solution. Now, this is a pretty wacky definition of linear dependence. The far more common definition is here, equation 9. But I think this here is, the null space definition is actually useful because it is, we've already talked about how to solve the null space problem. This problem here is a whole new problem, but it turns out that if you solve the null space problem, you solve this problem here, which is that the vectors are linearly independent if you can find some scalars, alpha 1 through alpha m, that are not all 0, where you can add these scalar multiples up and get 0. Right? So if all the alphas were 0, then this would obviously add up to 0. But we're requiring that not all the alphas are equal to 0. So for instance, maybe you have that x1 plus x2 equals 0. Then we would say that this list is linearly dependent. So if it's not linearly dependent, then we call it linearly independent. Are there any questions about this? Orb is typing in the chat, so I will wait a little bit. Yes, so the list of vectors is said to be linearly dependent if for some scalars, and importantly, not all of them can be 0. Then that linear combination of them equals 0. So another way of saying this is that if there are no non-trivial linear combinations that sum to 0. That's one way to think about it. Because, again, whenever I say there's a trivial case, I mean there's one very obvious case that's always going to be true, which is if you take alpha 1 through alpha m all to be 0. But if you're not in that trivial case and there exists a solution, then these vectors are considered to be linearly dependent. I see Ethan typing, so I'll move on for a bit and then you want me to? Okay, I can draw out. I guess I will draw out some. Can everyone see my screen with paint? Okay, so let's say this is this is 0, and these two vectors. These two vectors are linearly independent. And these two vectors are linearly dependent. So, because essentially, like, if I have one of these, I can get the other one. It's kind of hard to draw a three-dimensional example of this because I don't have Studio. But in 2 dimensions, it's just two vectors are independent if they're not in the same line. Two vectors are dependent if they are in the same line, going through 0. So that's the example in 2 dimensions. So I'm now going to use the language that we just talked about. I spelled course wrong. That's great. To redefine some terms. So earlier, we said that a subspace, if we take a subspace is defined as a span of some vectors, which is true. And the dimension of that subspace is the number of vectors that you get out when you run Gram-Schmidt. That was our definition of dimension. And this is true. And this is because what Gram-Schmidt does is it takes a list of vectors that might be linearly dependent, and it produces a list of vectors that are all linearly independent. And in particular, they're orthogonal to each other. And orthogonality guarantees linear independence. But you can have non-orthogonal vectors that are linearly independent, like we just saw with those two vectors in 2 dimensions. They weren't at 90 degrees from each other, but they were still linearly independent. So it turns out that you actually can define the dimension in a more general way. If I have a subspace of Rn, we'll call that subspace V. A basis of V is just any set of linearly independent vectors such that the span of those vectors is equal to the subspace itself. So for instance, we've used the term basis a lot. Gram-Schmidt produces a basis, as we've proved. The standard basis for Rn is a basis of Rn. And the dimension of V is just the size of that basis. And there's a remarkable theorem that I will not prove that states that actually, if you take any 2 bases of the same space, they must be the same size. So the dimension, that definition of the dimension actually makes sense. And so all Gram-Schmidt is doing is it's producing for you a very nice basis from an initial set of spanning vectors. And oftentimes you really want that nicest basis, which is what Gram-Schmidt gives you. Now, a consequence of this is that you cannot fit a larger dimensional space inside of a smaller dimensional space, which this might seem obvious, but because we actually haven't proven that until now. And theoretically, maybe, well, I guess we have maybe proven that with Gram-Schmidt, but theoretically, maybe there'd be a mathematical way of having a subspace of greater dimension than the space it's in, but this cannot happen. And the main way it cannot happen is through this idea of a basis. So I bring all this up because well, it's going to be very important for the kind of proof we're going to go through. Now, I'm going to preface this proof with a warning. My goal in showing you this proof is to show you what the kind of amount of work that goes into proving some of the results that we've left unproved. And I think it's valuable to see Now, I do not expect you guys to be able to like reproduce this. Um, uh, so just like before we get into it, just know that like if you can't like produce this proof off the top of your head, that's totally fine. I'm also not going to be as formal as I could be, especially at there's a part at the end, but the kind of this is the most important part of the proof. Um, and it's not too much harder than your homework, but there's kind of like a why would you even do this-ness about it. So here's the proof. So our goal is to prove that there can only be at most lambda, or there can be at most n unique values of lambda where ax equals lambda x has non-trivial solutions. Now, a great way of proving things in math is we have a statement, which is that we want to show that there cannot be, we want to show that there are at most n values of lambda where this has a non-trivial solution. One way to prove this would be to assume that there are more and show that we get a contradiction. Basically, show that if we assume that there are more than n solutions, then something in mathematics breaks. So that's what we're going to do. We're basically going to assume that there are n plus 1 solutions. There are n plus 1 unique eigenvalues of A, because these are called the eigenvalues of A. If any value lambda, I'm not sure if I mentioned it, any value lambda where this has a non-trivial solution is called an eigenvalue of A. So let's say you have n plus 1 unique eigenvalues of A. Then, well, what does it mean to being an eigenvalue of A? It means that there is a non-trivial solution. Let's call it xi. Oh, there should be an I there. Shoot. So there's some non-zero xi such that axi equals lambda I xi, right? So we call these xi's the eigenvectors of A with respect to lambda. Did I not define? I may have deleted my thing where I defined what an eigenvalue is. Whoops. I had a whole thing that I guess I deleted it. Whoops. Anyway, so now we just showed, right, that so n-dimensional space is n-dimensional, which means that any list of n plus 1 vectors must be linearly dependent. As if these were linearly independent, then it turns out that that n-dimensional space would have to be at least n plus 1 dimensional, which makes no sense. So we know for a fact that these n plus 1 vectors must be linearly dependent. So what I am going to prove to you now is that they must be linearly independent. And if I can prove that, then we have reached a contradiction, because a list cannot be both dependent and independent at the same time. Does everyone get the kind of or are there any questions about the kind of proof we're about to try and do, which is that we're going to try and basically prove that this list is simultaneously linearly independent and linearly dependent. Also, I'm actually not sure if Ethan has ever seen this proof. I'd be interested to know. Yeah, exactly. Well, these are linear, basically, if we took some number of those vectors and took their span, we could find the other one. It is the idea. Okay, so Now, what we're going to do, the proof strategy we're going to employ is we're going to take just some linear combination of these n plus 1 vectors, and then we're going to prove that each of these alphas must be 0, right? And if we can do that, that means that these must be linearly independent, because the only linear combination of them that reaches 0 is the trivial one. So that's going to be our kind of proof strategy. And it's a really slick argument, in my opinion. It's like it's kind of one of the like these really tricky things that once you like get it, it comes up a lot, which is, okay, what do we know about these vectors xi? We know that when we multiply them by the matrix A, we get lambda I xi, right? So if I multiply both sides of the equation by A, we're going to add a lambda 1 to x1. We're going to add a lambda 2 to x2. Sorry, multiply. We're going to multiply lambda n plus 1 times lambda n plus 1 times x to the n plus 1. Right? So that's what happens when you multiply by A. And this basically works because the A distributes over this linear combination. And then also A times 0 is always 0. But we can also multiply both sides of the equation by lambda n plus 1. And that gives us a different sum, right? So these two are different sums, but they both equal the same thing. So in fact, we can subtract these two. Which yields this equation here. I had to break it up into 2 lines because it was overflowing. Right, and so this lambda n plus 1 minus lambda n plus 1, this cancels. This goes to 0 because this is obviously 0. And so we get this new sum, this new linear combination of just n vectors. So we've basically gotten rid of one of the vectors, and we're still adding them up all to get 0. But the lambda i's are all unique, meaning that none of these other terms is 0. So there are two possible cases. Either alpha 1 through alpha n are all 0, in which case we can go back to the top, substitute in 0 for all these values, and then we just get that this vector here equals 0, which means that alpha must be 0, or alpha n plus 1 must be 0. Or at least one of these alpha i's is not 0. And because these are unique, that means that at least one of these coefficients, these new coefficients that we've gotten, must be non. The microphone went out. So we can do this again. We can multiply everything by A, and then multiply everything by lambda n, and then subtract, and we'll get another sum with n minus 1 vectors in it. And we can do it again, and we'll get a sum with n minus 2 vectors in it. And we can do it again, and we'll get a sum with n minus 3 vectors in it. And so if we do this n more times, or at least n minus 1 more times, then we'll get that alpha 1 must be 0. Alpha 1 has to be 0 all the way to, so what do we do now? Well, we go back to the start of this whole argument, and we replace alpha 1 with 0. Now we have a sum of n vectors. We run the whole argument again. That proves that alpha 2 must be 0. So now we have a sum of n minus 1 vectors to start, and we run it again and again. And so basically we run this whole argument again n more times. And if you do that, and this is the step that I'm basically like skipping over, kind of waving my hand. The formal way you do this is with induction, but like this step we proved lets you reduce the number of variables in this equation by 1. And so if you just keep doing it over and over again, eventually you'll reduce it to something simple. And so you can run this argument over and over again to show that alpha 1 is 0, alpha 2 is 0, alpha 3 is 0. You go on and on and on until you've shown that all the alpha n's must all be 0. But that means that the only possible sum that looks like this, where they sum up to 0, is if alpha 1 through alpha n plus 1 are all 0 themselves, which means that these vectors must be linearly independent. So we must have that this list of vectors is linearly independent, and we also must have that this list of vectors is linearly dependent. But this is a contradiction. And so something has to give, something has to break. And the only assumption that can break is that there are n plus 1 unique eigenvalues of A. That's the only assumption that can break. And so it must break. Because otherwise you have a contradiction, and you cannot have contradictions. So this is basically like the proof of this result here. Or no, sorry, of this result here. That an n by n matrix can have at most n unique eigenvalues. Now, there is another way of proving this. It's a more common way of proving it, but it's bad. It's bad because it's conceptually difficult and does not really drive home the kind of like reason this is true. So I like this proof better. Are there any questions about this proof? And like, yes, like again, if it didn't make sense, the kind of like main thing I'm trying to get at is that like once we've run this first argument, we've reduced this sum by 1 term, right? We completely eliminated 1 term. And we can just run the same argument over and over again until we've reduced it down to all the way to 1 term. And if we have like ax equals 0, or if we have alpha x equals 0, then either x is 0 or alpha is 0, and x isn't 0, so alpha must be 0. Yeah. Are there any questions about the proof? That's totally fair. Yeah, I debated about whether or not to mention or bring up this proof, but it is. I think for me, even if I don't understand the proof, it helps me to know that there exists a proof for a statement. Which my statement here is that a matrix A can have at most n eigenvalues. So I'll move on. Feel free to keep asking questions. But I'll move on for now to this discussion of multiple eigenvalues. So we've proven that this matrix can have at most n eigenvalues. But we haven't said anything about like a minimum number of eigenvalues it can have. And that's for good reason. If we use the argument we just used, then we've basically gotten as far as you can go with that. if you have an eigenvalue of A, then there's some eigenspace corresponding to that, right? It's like this null space that looks like this null space here. And we call the dimension of that null space the geometric multiplicity of lambda. So if that null space is trivial, its geometric multiplicity is 0. If that null space is non-trivial, then it could be 1, 2, 3, 4, all the way up to n. And so you could have, so for instance, the identity matrix, it has one eigenvalue. The only eigenvalue it has is 1. And that eigenvalue 1 has a geometric multiplicity of n. And so you can have these cases where you only have one eigenvalue. It turns out that you must have at least one eigenvalue, but you can have these cases where there's only one eigenvalue. But there is a way that we could count eigenvalues where we would always have n eigenvalues of A. Now, I just said that the identity matrix has only one eigenvalue, and I'm now saying that there's a way of counting eigenvalues where the identity matrix would have n eigenvalues. So what am I talking about? Well, unfortunately, and I thought long and hard about this. We have to talk about the determinant of a matrix. And so we're going to spend the rest of this lecture and a decent amount of next lecture talking about the determinant of a matrix. But it's basically going to come down to polynomials. So you all should have seen polynomials in algebra class. And it's possible for a polynomial to have a root with higher multiplicity than 1. So for instance, the polynomial x squared has a double root at 0. And so basically, it's going to end up becoming a root counting problem. And if you count roots by up to multiplicity is what we call it, a degree n polynomial always has n roots. And so it's going to turn out that because of this fact, an n by n matrix is always going to have n eigenvalues. But I'm getting ahead of myself because first we have to talk about the determinant. I love the determinant. I could not have said that statement until this year, but now it's one of my favorite mathematical objects. And it really is like a tremendous mathematical object, the determinant. But it also, a lot of times when it's presented, people just give you a formula for computing the determinant, and they try kind of to explain it, but they don't explain it very well. And the formula is terrible, and it's really takes a long time to compute the way that they give it to you, and so I just try and avoid it. So we're just going to kind of try and figure out why we even want the determinant, and actually try and figure out what the determinant formula might be just from the properties we want the determinant to have. So please ask lots of questions as we proceed. The first question that we want to think about is, okay, and this might be a strange question. Is there a test we could do on a matrix to figure out if it was invertible? Right, so not every matrix has an inverse. In fact, if its null space is non-trivial, it doesn't have an inverse. And so we want to run a test on a matrix to see if it's invertible. So what's this? We're going to call this function test. No, there are square matrices that are not invertible. Like if you take the identity matrix and you remove one of the ones, that is no longer invertible. The actual condition for whether or not, we've already actually discussed one, which is like the matrix A is invertible if it has a non-trivial null, if it has a trivial null space. But we'll get to that. So yeah, we want to define this function test, and it's gonna return 0 if matrix A is not invertible, and it's gonna return 1 if the matrix A is invertible. Okay, are there any questions about what test does? I haven't told you how to compute test. I've just said, let's suppose this function test exists. And I mean, it does exist. We could essentially attempt to compute its inverse, and if that fails, we return 0, and if it succeeds, we return 1. That would be one way of doing test. But I claim there's an easier way, or a more instructive way at least. Test is genuinely a mathematical function. It maps matrices into the numbers 0 and 1. Okay, and we're gonna talk about it like a mathematical function. So what are some properties of test? Well, the first one actually is that if A and B are both n by n matrices, then test of A times B is equal to test of A times test of B. This is because if A and B are both invertible, I actually can tell you its inverse, the inverse of their product, which is these two matrices here. And so basically, like, if A and B are both invertible, then so is their product, and so test of A times B equals 1. But then also test of A is 1, and test of B is 1, and 1 times 1 is 1. So these two are equal. And I'm not going to prove it now, but it turns out that if either A or B is not invertible, then their product is not invertible. There's basically no way to bring back invertibility by multiplying by a matrix. And so this makes it so that test of A times B equals 0, as does test of A times test of B, right? Because if at least one of these isn't invertible, then either test A or test B will be 0, and any number times 0 is 0. So test is what we call multiplicative. Basically, it distributes over matrix products, whereas matrices distribute over linear combinations. So it's not linear, it's multiplicative. Are there any questions about this slide? Okay. So that's the test function. Now we're going to talk about another function, which is the volume function. And I'm putting volume in quotes, but what volume is going to do is it's going to take in a matrix, and it's going to return the quote volume of the shape made by the columns of that matrix. So what does that mean? Well, I'm going to pull up Desmos this time. Actually, I prepared something for this. So let's say that the two columns of my matrix are given by this red vector and this green vector here. The volume I'm talking about then is actually the area of this purple parallelogram. I say volume because it's going to be like n-dimensional volume. So in 2 dimensions, it's area. In 3 dimensions, it's volume. In 4 dimensions, it's like hypervolume. And then, like, what do you even call, like, 5-dimensional volume? Well, mathematicians often just call all of it just volume. So it's like whatever dimension volume makes sense if you're talking in n dimensions. So I want to point something out, though. We talked about linear dependence. What happens if I make these vectors linearly dependent? Well, if they were truly linearly dependent, then this polygon, this parallelogram, goes from being a parallelogram to being a line. And lines do not have any area. So it turns out that volume only returns 0 if the columns of the matrix are linearly dependent. And I hope you'll take my word for it, because we haven't really proven it. We'll talk about this next week. That a matrix A is invertible if and only if, so basically it's necessary and sufficient for its columns to be linearly independent. So if A is invertible, then its columns are linearly independent. If its columns are linearly independent, then the matrix A is invertible. And so volume returns 0 if A isn't invertible, and it returns a positive number if A is invertible. Well, that's pretty close to test, right? All we have to do is apply what's called the sine function. The sine function sends negative numbers to -1, it sends 0 to 0, and it sends positive numbers to 1. And so it turns out that we actually could define test to be the sine function applied to the volume function of A. And this is test. Like, we've actually made a function that acts like test. Now, are there any questions about how we did that? The reason that volume can be used to determine if A is invertible is because of this fact here. So I guess we can talk about, so there's this big theorem in linear algebra called the invertible matrix theorem, and we can talk about it next week. But basically, the matrix A is invertible. Basically, if the columns of A are linearly independent, then A will be invertible. Moreover, the only way that the volume of A can be 0 is if the columns are linearly dependent. Right? As we saw in the 2D example, the only way to make that area go to 0 is to take those two vectors and have them be on the same line. The only way to have, if we had 3 vectors, so we're in 3D space, the only way for that volume to go to 0 would be for one of the points to be in the span of the other 2, right? And so the only time this can happen is if the columns are linearly dependent. And so basically, if volume returns 0, the columns must be dependent. If volume returns something other than 0, the columns must be independent. And so all we have to do is basically divide by the absolute value, essentially, but taking care to map 0 to 0. Does that make any more sense? Okay, cool. Um, and so basically by adding sine, this does the job. Um, and so an interesting uh, consequence of this is we know test is multiplicative. And we just constructed test by applying sine to volume of A, right? So does that mean that volume is multiplicative? Does that mean that volume of A times B equals volume of A times volume of B? Yes, actually it does. So you actually can, if you ever have A times B and you want to find the kind of evaluate volume of A times B, you can just take volume of A times volume of B. And to me, that's a pretty surprising result, and it's not super clear that it's true unless you use the fact that you already know test is multiplicative. Yeah, I mean, Borb, if you have another question, just feel free to ask. Um, ah, so Borb, you have predicted the future. The last step in our journey is the so-called signed volume function. So far, volume has always been positive, right? Volume is a positive number, or at least non-negative. But it turns out that we really actually care more about this notion of signed volume. First of all, the only difference between signed volume and volume is going to be the sign. So the absolute value of signed volume is just volume. So all we have to do now is figure out, given a matrix A, should signed volume be positive or negative? So the way we're going to do this is, right, in mathematics, one of the core ideas actually, and one of them, like it's like a foundation for multiple fields of mathematics. I'm over. That's amazing. Is that like everything that represents two states is like encodes the same amount of information. So like positive, negative, that's one piece, that's like one bit of information. True, false, that's one bit of information. That's literally where the word bit comes from. It's whether it's the amount of information encoded in a yes or no decision. So all we have to do is figure out something that has two possible states to figure out what our sign is going to be. And the rule we're going to use is, if I have a matrix A, and I switch any of the columns, I just flip two of the columns, I switch their places, then the signed volume will change sign. Now, volume isn't going to change, right? It doesn't matter what order we list the edges of a square, it's still going to have the same area. But signed volume, the sign will change. And so like a way of thinking about this is, in my case here, right now maybe the area is positive, but when I flip these two, if I flip these two, now the sign is negative. The area is negative. And so that's basically it, actually. We kind of need one more piece of information, which is that the signed volume of the identity matrix. And once you have that, we have basically actually uniquely defined signed volume, which might sound a little bit crazy because I've kind of only given you like one thing, but remember, the sign is only one bit of information. So it shouldn't take that much information to figure out the sign of signed volume. And that little bit of information you need is that the signed volume of the identity is positive. And from this, you actually can calculate the signed volume of any matrix. We're going to go into how to do that next time, but actually, this is the determinant. If you replace signed volume with det, that is the determinant. We have defined it, and we have not given a formula for computing it, but that's the definition. Or that's at least one definition. If you remember that like bell curve meme that Ethan shared in like his first lecture, this is very much a bell curve meme moment, because the kind of like left-hand side of the bell curve is like the determinant is the signed volume of the columns. The kind of middle thing is this like giant formula, and then the right-hand side of the bell curve is the determinant is the signed volume of the columns. It turns out to be like the correct way of thinking about this. So that's it for the lecture. I'll turn off the recording.